Okay, hello everyone. Thanks, Jay, for the introduction. I'm going to present our work, TaoStore, Overcoming Asynchronicity in Oblivious Data Storage, that we developed at University of California, Santa Barbara. Actually, I am lucky that Danny already wrapped up you regarding the ObliviStore and ObliviStore ideology. So, outsourcing private data has become increasingly more popular, and day by day, we see more cloud-based storage services. And after outsourcing the data, users access their data in terms of read and write manner, and these cloud storage services provide nice features. But how about the security concerns? The first thing that you can think about is the confidentiality of the data. We can ensure the confidentiality of the data by using the encryption. However, at this point, we need to ask the question whether the encryption alone is enough. Unfortunately, the answer to this question is negative. Earlier work showed that access patterns can leak sensitive information. To hide access pattern, we would like to achieve oblivious access. Basically, we are trying to find a way to translate each logical access to a sequence of random-looking accesses. ObliviStore is a standard approach to achieve oblivious access. And it was initially proposed by Goldrich and Ostrowski, and there is a huge body of work that achieves oblivious access. They usually store a secret state in terms of the storage information or at the client side. And the question here, are we done with this many of the questions? So the answer is no, because these are all single client constructions. And that was also one of the questions just before my talk, actually. We consider a different scenario here, where a company outsources its data to the untrusted cloud, and then the trusted employees will access this data concurrently. Here. And the concurrency, along with the concurrency, we would like to achieve security and the efficiency. The simple approach would be introducing a single ORAM client in the middle, and this can handle the client requests sequentially. But here we lose the efficiency because the access will be handled sequentially. And to date, we don't have so many solutions that leverage parallelism for higher throughput and efficiency. The initial work was the private FS that tried to provide parallel oblivious accesses to the cloud storage. Unfortunately, the private FS supports small number of concurrency. And then later on, ObliviStore system came up, and it introduced a proxy approach in the middle, where there is a trusted proxy in the middle, and it mediates the client request and handles the request concurrently by accessing to the storage. The more recent development is Curious that just came up, and it also follows the similar setting, and we also consider similar setting in our work. Another variable that affects the security and the performance is the asynchronicity. Unfortunately, earlier works does not capture the asynchronicity well, so this is what we are going to handle here. We have two main contributions in this work. First, we develop a security model for asynchronous ORAM and attack, and then we develop a TaoStore, which is a fully asynchronous and concurrent tree-based oblivious storage. Our threat model considers an honest but curious adversary model, where an adversary can seize the raw storage and all the network communication to the storage. In addition to that, the adversary can control the asynchronous links. So we cannot sure what the capabilities of the adversary, and we assume the worst case scenario that the adversary controls the messages, and it can delay the messages arbitrarily long. Another thing is that our adversary can schedule the operations at any point in time adaptively, and it also learns the response times of these requests. Earlier asynchronous ORAM security model was defined in the ObliviStore. It is inherently non-adaptive, and it doesn't leak the response time information. However, it is very hard to hide this information. The network might be intruded, or the response to the clients might trigger different behaviors, and there might be a side channel leakage. Therefore, we formalize the obliviousness in this setting. Basically, two time inconsistent executions should be indistinguishable. We have an indistinguishability-based security definition, which is called adaptive asynchronous obliviousness, or aaob security for short. But I will not get into the details here. Please refer to this paper for more details. So we have the aaob security. The question we need to ask whether the existing systems achieve aaob security. Bindschaedler and his team showed that ObliviStore has some security problems. And also, but Curious is secure in ObliviStore's threat model. Here, in this work, we show that Curious does not achieve aaob security. But we would like to note that no claims are incorrect in Curious. It just assumes a different security model. So I am going to show you that the Curious is not aaob secure. But first, let me cover briefly how the Curious system works. It partitions the storage space, and it has a modular design, actually. Each partition runs a single ORAM client, and every access happens to a random partition. Items are randomly reassigned after every access. And concurrent accesses for distinct items most likely will go to the different partitions. So here you see that we try to access item A and B, and these will be handled through different partitions. How does Curious handle when there are concurrent accesses on the same item? So Curious uses fake access approach. Only one real access will be made and the others will invoke fake or random accesses. So here you see there are two concurrent accesses on item A, and the second request will issue a fake access operation. Now we can present our attack against Curious. So here we consider two scenarios, actually. On the left case, we have two concurrent accesses on item A. On the right case, we have accesses on distinct items. The first request for the item A will issue a real access operation, but on the left case, there is a concurrent access on item A. So that will issue a fake access operation. But on the right case, we have an access on B that invokes a real read operation. So since the network is asynchronous and that it is under the control of an adversary, so we cannot know that whether the second request will be returned earlier or later, actually. So assume a scenario here, the response to the second request returned earlier than the first one. In this case, on the right case, the proxy will return a response for B, but on the left case, we cannot return a response for A because we haven't fetched it yet. Whenever we fetch the path for A, and whenever we fetch the item A, we will return responses for the request of A. As you can see, since the adversary knows when the responses are returned, it learns whether the accesses are on the same item or not. We have a fix for later, but just stay tuned, so we will show it to you later. So our second contribution is that we develop a TaoStore, a new fully asynchronous and concurrent tree-based oblivious storage. Curious is very good in terms of design. It is modular, but it has two drawbacks. As we've seen, so it doesn't support aaob security, and it achieves a concurrency by using partitioning. Underlying single ORAM clients are not concurrent. But we would like to achieve concurrency independent of the partitioning. We would like to achieve native concurrency even if there is just one partition. And the partitioning can be a simple add-on later on. Therefore, our solution, we developed TaoStore. It is a tree-based asynchronous oblivious storage, which is, of course, aaob secure, and it ensures atomic semantics. Additionally, it is simple, fully concurrent, and it enables easy partitioning. To date, we have too many tree-based single client ORAM constructions available, but the main challenge here is how to make tree-based ORAMs concurrent. Let me briefly go over the pet ORAM again and try to explain how it works. So this is a very popular tree-based ORAM construction. It organizes storage as a binary tree, and the nodes of the tree contains constant number of blocks. Every access happens to a random path, and the items are randomly reassigned after every access. This assignment information is stored in the position map at the proxy. It is possible to outsource this position map recursively, but however, we are not going to consider this in our model. When we want to access a block using the tree-based ORAM scheme, so it happens in 3 stages. When we would like to access item A here, we first need to fetch the associated path. Then we will do either read or modify operation, so that will either update the block A or not. But then what we are going to do, we will assign item A to a new random path in the position map. The second stage is the flush. We try to push every block to the lowest non-full node that intersects with its assigned path. In flush, however, we have 2 cases. The first one, if the root is not full here, we need to move A to a stash. The second case is that we can place the A into a subtree. Now the third phase. So after we are done with the flushing, actually, so we re-encrypt the complete path with fresh randomness, and we write it back to the storage. See, now we know how a single client tree-based construction works. So the question here we need to answer, how to handle k-concurrent requests. We would like to achieve concurrency. A simple approach would be first processing k operations. We fetch k corresponding paths to the proxy and form a subtree in the memory. The second stage, we will reassign k items to a new random paths. Then we will flush along the entire subtree, and then we will write the entire subtree back to the storage server in batches. By alternating between these 2 stages, we can have a nice solution. However, here there are 2 problems that these are very important. The first, how we are going to handle concurrent accesses on same block. The second question is, even we have a nice alternating structure here and nice system, flush and write-back operations are still blocking. We would like to achieve full concurrency, and let me here first consider our second problem first. We want to achieve non-blocking write-back. Even if there are ongoing write-back operations, we would like to continue processing. That is the motivation. However, it is not that easy. Let me give you a scenario here. We have a subtree in the proxy, and we would like to write it back on the server. Whenever we receive an acknowledgement, what should we do? In a sequential case, actually, we can just free up the memory. But here we are talking about concurrent case. There might be so many other things ongoing. So here the important question, what should we delete? It is not an easy question to answer, so let me give you an example for this case. We are at the time that we received an acknowledgement, and assume that we are waiting for a path that is shown with the blue dashed line. So what part of subtree that we need to delete? Consider a scenario, because the answer to this question depends. So assume the scenario that the write-back operation is processed at the server before a request is received, before it receives the request for the path request on the server. And then at this stage, the proxy will get the stale path actually, or will get the up-to-date and fresh path. There is no problem here. On the other hand, in the second case, actually, the write-back might be processed later on. So in this case, we are going to fetch the stale path to the proxy. There is no way for proxy to understand which of these cases happened on the server. So it will assume the worst case scenarios, and it needs to store the most up-to-date part of the subtree, and it will keep this intersection of the path on the proxy and delete the other part of the subtree. There are even more cases for the decision, but here I will skip all of these. The main motivation is that TaoStore achieves full concurrency by maintaining fresh subtree invariant. The items in the local subtree and stash are always up to date. And please see the correctness proof in the paper, actually. But we achieve full concurrency by maintaining fresh subtree invariant. And let me go back to my first problem. Concurrent accesses onto the same item. How we are going to fetch it? So we will use the fake access approach, as in curious. And now I can see that you are asking, wasn't there a problem wasn't there a security problem with that approach? That is why we introduced sequencer, whose whole function is ensuring logical requests to be replied in the same order as they arrive. Consider the attacking scenario that we have. The problem was that we return a response for the second request earlier than the first request. Here, actually, the sequencer delays the return, and all the requests are replied in the same order as they arrive. Note that this is a generic solution, and it can also fix the curious. In order to evaluate the performance of TaoStore, we perform cloud-based experiments. We use a 1 GB of data set, and we have a proxy at the UCSB, and we use the server from the AWS North California data center. Here, when there are 10 concurrent requests, TaoStore achieves a performance of 40 operations per second. When the number of concurrency increase, actually, we don't gain too much in the throughput because the throughput saturates due to the full bandwidth utilization. This shows us that bandwidth really matters in real-world scenario. Another set of experiments we conducted is that, so in order to see what is the effect of memory utilization to this performance. Here, K means the write-back threshold, so that after K path fetches, we are going to write back the entire subtree to the storage server. At this point, we have a 5%, when the write-back threshold is 240, we have a 5% memory utilization. Basically, which is the 5% storage utilization. This is compared to the overall data set size. When we have the write-back threshold is 40, and then at this point we achieve a throughput of 39, and this was also the case when the write-back threshold was 240. Even with a smaller memory utilization, TaoStore can achieve similar performance. In the first case, we have 5%. In the second case, we have 2% memory utilizations, but the achieved throughput is the same. This brings me to the end of my talk. Thank you so much for your listening, and now I am ready to take your questions.
We have time for a question. If there are no questions, I have a question for you. So, as Ian was asking, you do support multiple clients. It's my understanding, though, that they have to trust each other. Is that right?
The clients are trusted. So these are the employees of a company. You can assume in this way.
But what if they weren't? What if they were mutually distrusting? What if they didn't want each other to see their access patterns or the contents of keys?
Actually, the clients will not see each other's access patterns in this manner.
Okay, so they're
they
also
don't see others.
Is that proven, that the clients won't see the access patterns, won't be able to do anything about each other's access patterns?
No, they will not see. So you can assume that one of the clients can be an adversary. So the motivation is to hide the access patterns. So none of the clients will see the other client's access patterns. They will not be able to understand this.
I see. Okay, that's good. So you were assuming the attacker is local.
What do you mean by?
Sorry, the attacker has access to the local network. These clients all work for the same company, but the attacker has access to the internal network.
Yes.
Would there be other channels that an adversary with that much power aren't they probably
So
going to?
at this point, it is hard to understand what an attacker has, what are the capabilities. But the clients talk to a proxy through a network, actually. We assume the worst case scenario. It has an access over the asynchronous links also. That is the
But wouldn't an attacker that powerful have other side channels that they could exploit?
So the communications are encrypted here. So they might be, an attacker has other capabilities, but even it sees the messages, it will not understand actually. It will not get any information. So there will be a zero leakage.
Okay.
Okay.
Let's thank Cetin.
Thank you so much.